Gentlemen, I send you the virtual and the physical applause. Thank you, Moungi, Daniel, and JJ. Wonderful discussions and wonderful presentations. So welcome to the panel. One of the things that we've been talking about today is this interplay between clinical care, clinical practice, clinical research, but also innovation and entrepreneurship, spinning companies out of the technology that is coming out of our labs. So the meta question that I want to start with is, as you're looking at your research, how are you coming up with the problem that you're trying to solve? Are you having in mind a commercial pathway or a particular need that you're trying to solve? How did you get to the core of the problem that was interesting? So let's start with that high level. Maybe we can go in the order of presentations. Moungi, maybe I can go to you first, please.
Okay, sure. So the path towards the talk that I gave was a fairly nonlinear path. So we had material that was able to emit well in the long wavelength range, and that's a new material, so you could always think of a commercial path for that. And then accidentally, we discovered that there were actually fluorescence that was there from diseased tissue. We didn't expect to see it, but then we saw it, and then we tried to figure out what it was, and then we found that it was highly specific to a particular disease state, and that's where we went, and that was our discovery. Now, in terms of commercializing that, I think that for that particular discovery, a licensing direction is a more likely direction than a company based around that, because there's no really hardware. It's really an idea. The hardware exists already, and so it would be a licensing to a bigger company, I think, in this case.
Very good, thank you. The path is never straight, it seems. JJ,
never straight, yeah.
JJ, what are your reflections on the same?
So in our case, I guess it kind of comes both ways. Sometimes we have a hammer first. Sometimes we actually have a nail first. So specific to what I talk about in my presentation, the meta-surface optics technology. Initially, we were actually motivated by applications on the consumer electronics side. But then once we developed technology, there were actually medical doctors actually approach us, saying that this could have exciting applications in biomedical imaging. So that's kind of where we come along.
Thank you, JJ. Daniel.
Yeah, similarly, in conversations with radiologists, they often, they see robots doing amazing things, or they see things, they have their phones which have amazing capabilities already, and they say like, well, why can't we have this in MR or in CT or in PET or, yeah, and so obviously there are clear jumps from phone modality, mobile devices to a MRI machine, but this is essentially the pathway that they're asking for, and they have experience with commercialized versions of this for regular natural images. So similar, albeit more rigorous versions are slowly appearing at the market for medical imaging. Previous to an FDA guidance in 2018, a lot of medical imaging and artificial intelligence technology or machine learning technology was not as acceptable, but now it's there's starting to be more and more guidelines and more approvals. So yeah, that's where we're headed, and it's slowly coming along as other vision technologies also come along.
Very good, thank you. So another question that, and participants, please, as a reminder, we're getting some of the questions on the Q&A. That's the place to enter them. One of the questions, another meta question or high level, there's a lot of excitement worldwide with machine learning and data science. Was wondering if the speakers could speak to how they're using traditional signal processing or design techniques versus incorporating machine learning in various ways into the research. So again, a high level. Let's go maybe in reverse order. Daniel, I guess that just putting it on you for a moment, it was interesting you made the comment you can train it on one example. That's clearly not big data. But how would you classify sort of how you're using machine learning versus more traditional signal processing techniques?
Yeah, so a lot of the physics and chemistry and things that we can control in a scanner that we knew about before, right? They still apply. They're still real. And so we know quite a lot about physical motion. So in the presentation, we simply encoded a lot of the equivariances, so the guiding equations for physical motion into our machine learning model. The learning portion is about the image, but isn't about the motion, because we as humans and mathematicians already know quite a lot about that. So this same pattern could happen across other signal processing fields. That we did know quite a lot about these signals beforehand. So encoding these into learnable models is quite a nice trope, actually. It seems to improve efficiency quite a lot.
Very good. Thank you, Daniel. So JJ, are you designing with machine learning tools, or how is it machine learning influencing the work that you highlighted, or also in general?
You are right on the point. So we are using machine learning in several aspects in our work. So as you mentioned, we are actually using machine learning to perform design of this complex electromagnetic media. And the motivation there is that the electromagnetic response of this kind of structures can be very complicated and also non-intuitive. So having machines to kind of help us understand the underlying physics is actually something that's actually very beneficial and not easily achievable using the human engineers. So that's something we are doing here. Essentially, train using a large amount of data to feed into our design algorithms to train them so they can help spit out smart designs to enhance optical properties. Now, on the other side, once we have data coming out from imaging instruments, we are also looking into machine learning algorithms to essentially help improve the signal-to-noise ratio, help to extract specific features in the image along those kind of lines. So to essentially improve the intelligence capability of the entire system.
Thank you, JJ. And Moungi, how are you, or are you not using machine learning?
Well, we are. I have a student, Mari Saif, who led this project. So at the tissue level, where we do the imaging, there's a lot of more classical algorithms to sort of line up the images together. But then when we want to identify the pathological parts of the tissue, there's shape recognition. So that goes on. And so we are using machine learning to distinguish between the signals that come from the disease part, which are more globular, let's say, from normal tissue, which is more looks more like filaments. And so there's that training going on there also. So we definitely are incorporating machine learning into the image processing.
Very good. Thank you for that. So I'm going to take a few questions that are targeted at each one of you individually to drill down into a little bit more. The question here from Moungi, how would this work on humans? You gave examples on the mice, in vivo and biopsy. What's the pathway to human use?
So I think for the human use, it's in pathology at the tissue level slice, which I alluded to at the very, very end of the talk. And we are actually working with pathologists at MGH, group at MGH. We're going through many human tissue slices to understand if we can diagnose and grade the tissue through the autofluorescence in the square, and on top of that, putting in the machine learning aspects of it. So that's where the human applications, I think, are the first ones to go. Humans are a lot bigger than mice, obviously, so light doesn't penetrate very deeply in humans, relatively speaking. So I think it is at the biopsy and the tissue level that the applications to humans are going to take place. We could go and bring in a probe, but that would be surgery basically, and so that limits things. for this particular application.
Okay, very good. Thank you. So I think, let's see, take this question up, scroll up here. For JJ, the question's in the space of the materials. Like, is it possible to make a flexible variant? And what would that mean if it were flexible? And then also the second question is, well, are we able to get samples to try?
Okay, so about the first question, so I think we can definitely make this devices flexible, and there's immense opportunities in terms of applications if we can make it flexible. So some examples would be if we can actually integrate it, for example, a curved surface, we can actually get an imaging instrument with a field of view actually exceeding 180 degrees. We can go to something like 270 degrees within our design here. In addition to that, if it's flexible, we can also envision integrating them on, for example, flexible endoscopes or epidermal devices, such that you can enable different kind of imaging modes. And what was the second question?
Are you able to give out samples, or can people try something in a system or a setup that they would like to experiment with?
Yeah, so we have samples. We are definitely very much welcome collaborations. It would be even better if we can understand about what are the specific needs that you will have. Then we can actually kind of custom design and fabricate samples specific to your application.
Thank you. And then Daniel, the question here was, how would this work, or is the framework extendable if you allow deformations? So not just the rigid body, but allow some kind of flexibility in the object or objects that you're tracking.
Yeah, so for the deformations that we easily understand, so in the magnet, as you go away from what's called the isocenter. So if you're in the MRI machine and you move your head up, your image will deform a little bit, and we understand that pretty well because it deforms based on the magnetic field. So we can deal with those pretty well. But for larger deformations, so we're looking across subjects, there are other models. Voxelmorph is probably the most popular. But the equivariant framework I was talking about earlier probably will not work simply because we don't understand diffeomorphisms well enough. But for tracking, this should still work out because we're guaranteed that the subject is the same. So we're sort of guaranteed a rigid motion, or at least we hope that your brain is not moving non-rigidly. So something's going wrong, right?
True. After the last couple of days, I may have a little deformation going on. So let me actually take it back to another high-level question. One of the things I've been asking the panels in general, and you may have already answered this, or at least a part of this, when articulating how you identified the research questions. But what have been the biggest surprises? Wisdom, as I said yesterday, is what you get when you don't get what you expected, or that's experience, I guess. What are the things that were surprising along the way that you say, oh, it worked that way, or oh, that's the new direction to take? What are those surprises that have come about as you've been executing these various research paths? I'll go JJ in the middle since I've been putting him in I'll go with JJ first because he's been in the middle, both directions here.
Sure. I think what's really exciting is always this kind of serendipitous discovery about some exciting new applications that you can never think about. So like I mentioned, when we first came up with the idea of the fisheye flat lens, we were really thinking of having consumer electronics in mind, like for cameras or consumer electronic devices. And then we actually kind of presented the work at one of the MIT conferences. And then we have medical doctors approaching us saying like, this will actually be very good for imaging the human retina. And that's an application I have never thought about at all, or like why it's even relevant. So we then look into it, figure this is actually a very promising application. We kind of now look into it. This is one of the major applications I'm looking at right now. So I think having this kind of industry, academia, collaboration and communication is really exciting and allow you to discover a lot of exciting applications and expand about your conventional expertise to look into exciting new fields.
Very good. Thank you, JJ. So let's go, Daniel. What surprised you along the way?
Yeah, it's in a similar vein. Simply speaking to a large number of radiologists, they come up with great ideas, and quite often as a computer scientist, you feel sort of almost a conservative, like, oh no, that sounds impossible, nature, right? Like, oh, that sounds like quite a leap. And then you follow them, and it turns out their ideas are intuitionally correct, but also work out quite well. So, follow your field experts is what I've learned from this. And even if they're, you speak one language and they speak another, they know what they're talking about. So they probably have great guidance for you, just for which direction to go next. Yeah.
Very good. Thank you, Daniel. And then Moungi.
Yeah, so this work that I described is a part of a collaboration, long-standing collaboration with the Jane group at MGH. And we don't really know that much about disease models and things like this, but they do. And so we bring in an expertise that they don't have. And it's really the combination of the two that is successful. And as I mentioned, the surprise was by shining our light into a mouse that happened to have a diseased liver and seeing it glow. And that was like, wow, what's going on here? We didn't expect that, right? That was a total surprise. And then the second surprise was when we went to human tissue. And that should not have surprised me, because I've worked enough with animal models and humans to know that humans are not mice and vice versa. But at the tissue level, the humans behaved exactly the opposite from the mice. And so that's really exciting and interesting. And that's really a surprise.
Indeed, we're a little bit bigger than mice. So
and not just bigger, but we also live a lot longer than mice. And that makes a huge difference in terms of what can pile up in your organs, et cetera, all the metabolites that go on. Mice just don't live long enough to see the things that we see in humans.
Very true. They probably also don't have as much adult beverage either to sort of do damage to the liver. So this is your opportunity. I want to sort of close the panel with, what are the one or two burning questions that you would love a clinician or a collaborator to reach out and say, hey, I'm really interested in this, or I need to know this. What are the connections that you want to advertise, that you want to make? Who do you want to contact you and why? Let's go with JJ again, since I'll put you in the middle one last time.
Okay, I guess I would kind of want to welcome kind of more feedback from the clinical side about what are the exciting or maybe difficult imaging problems that you have in mind that we may be able to contribute to. I think, like I said, so having being exposed to this kind of problem-rich environment will be very, really exciting, and we are always looking forward to extending our work into the field of biomedical imaging.
We'll go around the table. Daniel.
Yeah, I think a burning question or a burning desire, like we do adult human brains in Western populations really well now. What's next, right? What are the hard populations? We know stroke is difficult, tumors are difficult, but in the clinic, we see quite a lot of different other diseased phenotype populations. What's giving trouble? These are the adversarial examples that we need to build off of. What's next, I guess, is the question.
Very good. Thank you, Daniel. And Moungi.
Yeah, sure. So one part of it is easy. So what we've discovered is a way to non-invasively follow and track a disease, which is a very important disease of the liver today. And so I want to reach out to the drug developers that have to sacrifice, hundreds of mice, and I want to shorten your time to get a hit on your drugs, time and money. So I want to help you with that, with my technology. And the second thing, to the clinicians, I want to know more about other diseases that form similar metabolites, steroid-like metabolites, where we could help with imaging non-invasively, both preclinically, but also at the tissue level.
Very good. With that, I hope you get inundated with very spot-on outreach. And again, I applaud you for your time, and I thank you for your time and attention and the phenomenal research and in your words of sharing and wisdom. So that concludes this panel, this session.